So let's continue with what we were doing, and this time we will do the quicksort algorithm. We have seen that quicksort algorithm runs in time n log n when the array size is n. Okay. So how do we do this? So if you go back to the lectures and check how quicksort was done, it's a recursive procedure or inductive procedure where you pick an array and then you have to pick an element in between arbitrarily, but then you have to be able to say which elements are to the left, which elements are less than or equal to that element, and which elements are greater than or equal to that element of that arbitrary element that you pick. Is that okay? So in our algorithm, we will make a convention that the arbitrary element that we pick will always be the rightmost element of that list, which is the last element of that list, always. Okay, the last element of the array. So just as before, let me just copy. So we are given an array A1 to n. Okay. So first, it's about finding this left and right parts of any given array, right? So let's write down this function. Let me call it a partition function. Okay, and the input is just the array A. Right. So once again, start. Partition function. Is that all right? What is this supposed to give as output? This is supposed to give as output the left part, the right part, and the arbitrary middle element of this array A. Is that okay? That is what this is supposed to give us. All right. So let's do that. So how do we do this? So A at A dot length is the element that we select out. Okay. So let us start by creating two smaller arrays. Okay. Create, let's call it left array and right array. Okay. So L. So now here's the thing. It's array, but it is better if we think of it as a queue. Okay. So let me write create queues. Left. So left queue, right. Okay. But at this point, what are the queues? The queues are empty because we have not entered any element into this queue. Okay. Create queues, left queue and right queue. So these are two queues that we will create. But these are empty. Okay. They just have the pointers. They have the head and tail pointers. That's all. Nothing else. Correct. And you know what an empty queue is because we have already seen this function queue empty. It will output a value true or false, depending on whether it's empty or not. Right? So that is what it is. So instead of arrays, we will work with queues because queues become much more convenient for us. Is that all right? So now what do we do? So we have created queues, left queue and right queue. And now we simply do this. So for, let's say I go from 1 to a dot length minus 1 because a at a dot length is a separate entity for us. Okay, we we want to distinguish that element. All right, so we will only go up to a dot length minus 1, and now we will compare. Okay, how do we compare? So if a at I is less than a at a dot length, this is where we are using the last element. Okay, we are comparing every other element with the last element. So if it is less than the last element, we will put this in the left queue. So what was the function for including an element in the left queue? Let's go back. It was this function nq. Nq, name of the queue and the element that we will enter. Okay. So we will enter nq, sorry, nq into which queue? Into the left queue. which element a of I. Is that okay? If that's not the case, if a of I is greater than or equal to a of I, else we do nq into the right q, yeah, and we do this for every element. Is that okay? Alright. So now these elements are all there in these two queues, except the rightmost element, which we don't know where to fit. So now what we do is, now we will sort of rewrite elements in A from these queues. Rewrite the elements in A from these queues. So we can do it for the queue A itself. So, but instead let us free a new space and do it for B. So create, we're creating an array B, 1 to 8 of A. That is okay. And now how do we enter elements? So for I is equal to 1 to 8 of length. Alright. Not 8 of length. Sorry. Very well, sir. So how do we enter the elements? First the elements in the left queue, then the element, the distinguished element, and then the element in the right queue. Is that okay? So for I equal to 1 to left queue dot length. How do we enter this element? In just the same order as we entered it into the queue. So now DQ, we have seen DQ. DQQ, we don't even need to mention which element. We will just pop out the element according to the order. DQ, Q. Okay, but this element is popped out, right? If you look at this element is returned. Okay, have we returned an element here? Yeah, it returns the element out. Okay, but where will we put this element? We will put this element at vi. Okay, the element which pops out of dq, we put it inside vi. Okay? And for then, before we go next, we have to put the last element of a at the next place. So which is that place? B at left q dot length plus 1 is equal to a at a dot length. Alright. And then for the remaining indices, I equal to q dot length plus 2. 2. How much? Well, you know how much it's going to be. It's going to be up to 8 dot length. Okay. But which element will you pick? Again, BF5 is equal to, now you DQ the right. Is that okay? And for. Okay, so this way the new element, the new array B is created, and now we'll just return this out. So return, but we need to return both. We need to return B as well as the index at which the A dot length, the last element, the arbitrary element that we pick, that is placed. That is placed at the location fq dot length plus 1. Okay. So we will return that value as well. Fq dot length plus 1. Okay. This value we need to. So the output of this algorithm is a pair. It's an array and this location of the distinguished element. Okay, such that everything to the left is going to be less than or equal to the element at this index. Everything to the right is going to be greater than or equal to the element at this index. Okay, this completes the partition function. Now, are we ready to do quicksort? Yes, because this was the inductive part. Remember, this was the inductive part inside. So now we can go ahead and do partition. Sorry, quicksort. So let's do B. Quicksort. Okay, right here now. What do we first do? It's an inductive algorithm, right? It's an inductive algorithm. The first thing that we do is nothing. We just do this. So let's take these values B, and this is a pointer R. B and R is equal to partition A. Is that okay? B and index R equal to partition A. So we get these two parts, right? But now we can replace this, right? B is the sorted form. So what we do is the elements of A are all there in B. It is just that they are now sorted up to this in this way. The rth index is holding the last element of A. Everything to the left of R will have the elements less than A of A dot length. Everything to the right of R will have elements greater than or equal to A of A dot. But the elements are the same. As a set of elements, the elements in B is the same as the elements in A. So I'll simply first replace the elements in A with the elements in B, which means I have gone one step ahead and I have done the first partitioning in A itself. Okay, I've replaced it completely. Okay, but now what do I do? Now I need to repeat quicksort. But I repeat quicksort on what? On the smaller parts that I've got. The left part up to R minus 1 and the right part from R plus 1 to N. So that's what I do. The repeating exactly looks on the smaller parts, right? So A from 1 to R minus 1 is equal to quicksort applied on A at 1 to R minus 1, right? So what am I doing? I look at the left part, the part to the left of R in A, apply quicksort on it, and the output I'll pass it back to A itself. So that part gets sorted. Similarly, R plus 1 to A dot length is again equal to quicksort R plus 1 to A dot length. Why is that? So I'm not touching A of R because A of R I don't want to touch. A of R was a distinguished element and I have fixed its location. Its location is here, given by this partition function. Okay. Now I'm applying the quicksort algorithm repeatedly only on the left and right blocks. The arbitrary element which got fixed at a particular location remains as it is. That's what we do in quicksort. Right? So this is induction because the rth index is going to be roughly half at the halfway, and now these two quicksorts are now applied on smaller two arrays of half length, and then you keep dividing. Okay, so inductively, this will give you the sorted array. Is that okay? So now we have already done this with diagrams, and now this is the actual algorithm. Now what I want you to do is pick the example from the lecture. Okay, and now do quicksort exactly as per this algorithm. Do quicksort exactly as per this algorithm. Okay, and see how it happens. Okay, it will happen exactly the way we did it. Okay, So that completes Quicksort. Okay. Now there is a small uh, exercise that I want to give you, which is this part. So this. All right. So let's just do this much exercise. I'll do later. Okay. So the exercise was about runtime, but you already know. So let me just write a remark. We know that Quicksort runs in time order n log, okay, where n is the length of the array that we already know because given an array a1 2. Okay, so that completes Quicksort. So we'll stop here for now.